Let's understand why the equation 5x plus 4y equals 9xy is not correct. Here's our equation. One way to check if an equation is correct is to try some simple values for x and y. Let's try x equals 1 and y equals 1. Let's substitute these values into both sides of the equation. On the left side, we have 5 times 1 plus 4 times 1, which equals 9. On the right side, we have 9 times 1, which also equals 9. Well, this seems to work, but let's try another set of values. Let's try x equals 2 and y equals 2. On the left side, we have 5 times 2 plus 4 times 2, which is 10 plus 8, equals 18. On the right side, we have 9 times 2, which is 9 times 4, equals 36. 18 does not equal 36. Let's understand why this happens. On the left side, we have linear terms, 5x and 4y. These terms grow linearly with x and y. When we graph linear terms, they form straight lines. But on the right side, we have 9xy, which is a quadratic term. This grows much faster than linear terms. When we graph quadratic terms, they form curves that grow much more quickly than straight lines. Let's look at how these terms grow. When x and y are 1, both sides equal 9. When x and y are 2, the left side is 18, but the right side is 36. When x and y are 3, the left side is 27, but the right side is 81. The right side grows much faster than the left side. This is why the equation cannot be correct. The left side grows linearly with x and y, while the right side grows quadratically. It's impossible for these two expressions to be equal for all values of x and y, except in very specific cases like when x and y are both 1, or when x and y are both 0. Remember, when checking if an equation is correct, try different values. If you find even one case where the equation doesn't work, then the equation cannot be correct. Let's learn how to factorize the expression 4x plus 16 and understand why the answer is 4 times the quantity x plus 4. Let's start by writing out our expression, 4x plus 16. To factor this expression, we need to find the greatest common factor of all terms. Let's break this expression into its individual terms. We have 4x and 16. Let's look at the first term, 4x. We can break this down into 4 times x. For the second term, 16, we can write this as 4 times 4. Now, we can see that both terms have a common factor of 4. Let's highlight the common factor in both terms. When we factor an expression, we take out the common factor. In this case, we can factor out 4 from both terms. This gives us 4 times the quantity x plus 4. Let's verify this is correct by distributing the 4 back through the parentheses. When we multiply 4 times x, we get 4x. And when we multiply 4 times 4, we get 16. Adding these terms together gives us back our original expression, 4x plus 16. So, to summarize, when factoring an expression, we look for the greatest common factor of all terms. In this case, both 4x and 16 share a common factor of 4. By factoring out this 4, we get 4 times the quantity x plus 4, which is our factored expression. Let's examine why the statement, a plus 4 times a plus 2 equals a squared plus 8 is incorrect. We'll do this by properly expanding the left side of the equation and comparing it to the right side. Let's start by using the FOIL method to expand the left side of the equation. FOIL stands for first, outer, inner, last, which helps us remember how to multiply two binomials together. Let's create a diagram to show how FOIL works. Let's expand this step by step. First, we multiply the first terms. A times it gives us a squared. Next, we multiply the outer terms. A times 2 gives us 2a. Then we multiply the inner terms. 4 times a gives us 4a. Finally, we multiply the last terms. 4 times 2 gives us 8. Now let's combine like terms. The 2a and 4a terms can be combined to give us 6a. So our final expansion is a squared plus 6a plus 8. Let's compare this to the original statement. The original equation claimed that a plus 4 times a plus 2 equals a squared plus 8. However, we can now see that this is incorrect because we're missing the 6a term in the middle. This is a common mistake when expanding binomials, forgetting to include all the terms that come from the FOIL method. The correct expansion of a plus 4 times a plus 2 is a squared plus 6a plus 8. Remember, when multiplying binomials, always use the FOIL method to ensure you include all terms in your expansion. The middle terms are just as important as the first and last terms. Let's solve this problem about finding the greatest common factor of 5a and 15b. We need to find the greatest common factor of 5a and 15b. Let's break this down step by step. First, let's identify all the factors of 5a. The factors of 5 are 1, 5a, and 5a. Next, let's find all the factors of 15b. The factors of 15b are 1, 3, 5, 15b, 3b, 5b, and 15b. Now, let's identify the common factors between these two expressions. Looking at our lists, we can see that 1 and 5 are the only common factors. The greatest common factor is the largest number among these common factors. Therefore, 5 is the greatest common factor of 5a and 15b. Let's verify this is correct by showing that 5 is indeed a factor of both expressions. 5a divided by 5 equals a. 15b divided by 5 equals 3b. Since both divisions result in algebraic expressions with no remaining numerical factors, 5 is confirmed as the greatest common factor. Let's look at a real-world application of greatest common factors. Imagine you have 5 apples in each basket and 15 bananas in each box. If you want to distribute these fruits equally among students, the greatest number of students that can receive whole numbers of both fruits would be 5 students. Each student would receive 1 apple and 3 bananas. Therefore, looking back at our multiple choice options, we can confidently select option C, which is 5, as our answer. Let's learn how to factor the expression x cubed minus 25x. We'll break this down step by step to find the complete factorization. The first step is to identify the greatest common factor of all terms. Let's look at our terms x cubed and negative 25x. We can see that x appears in both terms, making it our greatest common factor. Now, let's factor out x from both terms. This gives us x times the quantity x squared minus 25. Now, looking at what's inside the parentheses, x squared minus 25, we can recognize this as a difference of squares pattern. Remember, a difference of squares follows the pattern as squared minus b squared, which factors to a plus b times a minus b. In our case, x squared minus 25 can be written as x squared minus 5 squared. Therefore, it factors to x plus 5 times x minus 5. Putting it all together, our complete factorization is x times x plus 5 times x minus 5. Let's verify our answer by expanding it back out. First, distribute x to x plus 5, then distribute that result to x minus 5. This gives us x cubed minus 25x, which is our original expression. To summarize, we factored this expression in 3 steps. First, we factored out the greatest common factor, x. Then we identified x squared minus 25 as a difference of squares. Finally, we factored that difference of squares to get our complete factorization, x times x plus 5 times x minus 5. Let's solve this algebraic expression by factoring. We'll use the method of factoring by grouping to simplify a squared plus bc plus a plus ac. First, rearrange the terms for easier grouping. Let's rearrange this as a squared plus a plus ac plus bc. Now, let's group the terms. We'll group a squared plus a and then ac plus bc. Notice how we've split this into 2 groups. Let's factor out common terms from each group. In the first group, a squared plus a, we can factor out an a. In the second group, ac plus bc, we can factor out c. Now, we can rewrite our expression as a plus b plus c, a plus b. Notice the common factor, a plus b. Factoring out a plus b, we get a plus b, a plus c. Let's verify by expanding. A plus b, a plus c, equals a superscript 2 plus ac plus a plus bc. This matches our original expression, confirming our factoring. Let's learn how to factor this expression using the difference of squares formula. We're given the expression as squared over 4 minus b squared over 9. First, let's recall the difference of squares formula. When we have an expression in the form x squared minus y squared, it can be factored as x plus y times x minus y. To use this formula, we need to identify the perfect squares in our expression. In our case, we have a squared over 4 and b squared over 9. Let's rewrite these as perfect squares. Remember, a squared over 4 is the same as a over 2 squared, and b squared over 9 is the same as b over 3 squared. Now our expression is in the form of a difference of squares, where x is a over 2 and y is b over 3. Let's substitute these into our difference of squares formula. We get a over 2 plus b over 3 times a over 2 minus b over 3. This is our factored expression, but we can verify it's correct by multiplying it back out. Let's use the FOIL method. First, outer, inner, last. First terms, a over 2 times a over 2 gives us a squared over 4. Outer terms, a over 2 times negative b over 3 gives us negative of over 6. Inner terms, b over 3 times a over 2 gives us a over 6. Last terms, b over 3 times negative b over 3 gives us negative b squared over 9. When we combine like terms, the middle terms cancel out because they're opposites, and we're left with a squared over 4 minus b squared over 9, which is our original expression. Therefore, the factored form of a squared over 4 minus b squared over 9 is a over 2 plus b over 3 times a over 2 minus b over 3. This factorization demonstrates a key application of the difference of squares formula with fractional terms. Remember the key steps. First, identify the perfect squares, rewrite them in squared form, then apply the difference of squares formula. The factored form can always be verified by multiplying. Let's solve this problem step by step to find which expression has x plus 1 as a factor. First, let's recall that x plus 1 can also be written as x plus 1 superscript 2. Let's expand x plus 1 to see what it equals. When we multiply x plus 1 by itself, we get x superscript 2 plus 2x plus 1. This is a perfect square trinomial. Now, let's compare this expanded form to each of our options. Option A is x superscript 2 minus 1 plus 2x, which can be rewritten as x superscript 2 plus 2x, 1. This is not the same as x superscript 2 plus 2x plus 1. Option B is x superscript 2 plus 1 minus 2x, which can be rewritten as x superscript 2, 2x plus 1. This is also not the same. Option C is x superscript 2 minus 2x plus 1. Again, not the same. Option D is x superscript 2 plus 2x plus 1. This matches our expansion exactly. Let's visualize this geometrically to understand why. X plus 1 superscript 2 equals x superscript 2 plus 2x plus 1. We can represent x plus 1 superscript 2 as a square with side length x plus 1. When we break this down into areas, the top left square has area x superscript 2, the two rectangles each have area x, and the small square in the corner has area 1. Adding these areas, x superscript 2 plus x plus 1 equals x superscript 2 plus 2x plus 1. Therefore, we can conclude that option D, x superscript 2 plus 2x plus 1, is the correct answer as it is equivalent to x plus 1. Let's solve this factorization problem step by step. We need to factorize the expression 25x squared, y minus 5xy. The key to factoring is to first identify any common factors between all terms. Let's look at our terms separately, 25x squared y and negative 5xy. Looking at these terms, we can see they share some common factors. Let's break down each term into its factors. In the first term, we have 5 times x times y. In the second term, we have negative 5 times x times y. Now, looking at both terms, we can see that 5xy appears in both terms. This means 5xy is our greatest common factor. Let's factor this out. To find what goes inside the parentheses, we divide each term by 5xy. For the first term, 25x squared, y divided by 5xy equals 5x. For the second term, negative 5x, y divided by 5xy equals negative 1. Therefore, our factored expression is 5xy times the quantity 5x minus 1. Let's verify this is correct by distributing back. Let's see a real-world application of this type of factorization. Imagine you're designing a rectangular garden where the length is 5x meters and the width is y meters. The expression 25x squared, y minus 5xy can represent the difference between two garden areas, one that's 5 times larger in length and the original garden. When we factor this expression as 5xy times 5x minus 1, we can interpret it as 5x, y representing the base area of the original garden, multiplied by the factor that shows how many additional base areas we're adding or subtracting. This factorization helps us understand how the difference between these two garden areas relates to the original garden's dimension. Let's solve this factoring problem step by step. We need to factor a to the fourth minus b to the fourth. The key is recognizing this as a difference of squares, but with higher powers. Let's break it down. First, rewrite ab as a difference of squares. Think of it as a superscript 2, b superscript 2, superscript 2. Now, use the difference of squares formula. P superscript 2, Q superscript 2 equals P plus Q, PQ. Here, P equals a superscript 2 and Q equals B superscript 2. Notice a superscript 2, B superscript 2 is also a difference of squares. We can factor this further. Substituting this back, we get the complete factorization. A superscript 2 plus B superscript 2, A plus B, AB. Let's check our options. Option B matches our answer perfectly. Here's a real-world application. Imagine nested squares with side lengths A and B. The difference in their areas is AB. In summary, we factored A, B using the difference of squares twice.